MonB5G is an acronym for the H2020 5GPP ICT20 project titled Distributed Management of Network Slices in Beyond 5G. It provides a zero-touch management and orchestration platform to support large-scale network slicing and automatically manage the underlying communication networks without human intervention for 5G and beyond. The MonB5G system emphasizes security and energy efficiency, providing a distributed and scalable architecture for next-generation networks. A data-driven system relying on artificial intelligence techniques is deployed to distribute management and operational tasks throughout the network. Because of its design, it can adapt to changing conditions in real time and use artificial intelligence-based techniques to detect and mitigate attacks on the network to improve security and reduce reaction time thanks to a local decision-making process. In summary, the MonB5G system will enable network operators and service providers to offer a wider range of high-quality services to their users with a focus on adapting to new needs and delivering high-quality experiences.
MonB5G architecture consists of two layers: management and orchestration and infrastructure layers. MonB5G identifies, detects, and mitigates attacks within and between slices, thanks to monitoring system, analysis engine, and decision engine. Monitoring system collects the number of user equipment attach requests from the 5G core network. The monitoring system formats the data and sends it to the analytics engine that leverage the gradient boosting algorithm to compute a detection rate for each user equipment. The detection rate value will be used by the detection engine to decide whether to blacklist the user. MonB5G system is able to detect and mitigate distributed denial of service attack. Abnormal traffic is started. Monitoring system starts receiving the attach requests from user equipment, while the analytics engine starts receiving formatted data containing the subscription permanent identifier and timestamp of users. After the event, in the decision engine appear the list of users associated with their detection rate. When the detection rate exceeds a defined threshold, the user is blacklisted, not being able to attach again. MonB5G solution was able to detect the users participating in the attack and blacklist them. In the top are presented result for normal traffic, in the bottom for abnormal traffic. Points correspond to the event data, while the green line represents the anomaly interval. If a point is outside the green limit, it is considered an attack. Banning a relevant part of the devices taking part in a distributed denial of service attack is enough to mitigate it. In this scenario, each running network slice is managed locally by a domain slice manager, which includes a monitoring system and an analytic engine, while an inter-domain slice manager is in charge of the management and orchestration of network slices. To ensure privacy, running network slices only share their model parameters with the central inter-domain slice manager, where are aggregated to build a global model. However, federated learning can be exposed to poisoning attack. MonB5G proposes a new framework to mitigate poisoning attack by detecting malicious participants in the federated learning process by using deep reinforcement algorithm and unsupervised machine learning. Demo demonstrates that MonB5G proposed approach is able to detect and mitigate the poisoning attack on the federated learning. Through federated learning rounds, the monitoring system collects the weights matrix. At the fourth federated learning round, the monitoring systems sends the weights matrix to the analytic engine. The latter applies dimensionality reduction on the received weights matrix from the federated learning nodes. As a result, the weights matrix can be presented as two dimensions thanks to the dimensionality reduction algorithm. As it can be seen in the plot, the updates of nodes, the weight matrix, present two different groups. Decision Engine classifies the output of the analytic engine into two clusters using k-means clustering algorithm. It results in two different lists of the federated learning clients, one for the trusted and other for the untrusted federated learning clients. Federated Learning Server continues the training with trusted clients only. Mean squared error metric decreases as federated learning rounds are increased, even when an infected model is injected due to the application of dimensionality reduction and clustering scheme to detect and remove infected models. MonB5G detection scheme enables not only to identify malicious domain slice managers, but also to improve the accuracy of the global federated learning model. MonB5G proposes zero-touch management that is able to detect and mitigate attacks without human intervention.